All right, here in the try class, just like always, we need two methods. A public method to kick off the recursion. So public void remove. We give it a string and another method that does all the recursive work. So remove, we give it a node called root and the same word. Now in our public method, we simply call remove, give it a root and this word. Now in this private method, we are at this root object. We need to find one of its children because we have to walk down the tree until we find the last node for the last letter of this word. But which child? We have to know what character in this word we are looking at. So here we need another parameter, integer index. And initially, we pass 0 here because we're visiting the first character. Now, before we call this method, we need to know what character we're looking at. So that is very easy. We simply call word.char at this index. This will return the character, and then we pass it to this method. With this, we get the child object. And this is where we need to recursively call the remove method and visit each child until we get to the last child or the last node for the last letter of this word. However, it is possible that at some point, child becomes null. If we try to remove a word that doesn't exist in our tree, this child object is going to be null. So we have to check for that. If child is null, we're going to stop right here. Now, we could also throw an exception, but I think that's a little bit too aggressive. I would rather to return silently. Not a big deal. Now, at this point, we have the child object. So we recursively call the remove method, give it this child node, the same word, and the next index. So this is the recursive part. Now, at some point, we want to stop the recursion. This is where we need the base condition. What is our base condition here? When we reach the last letter of this word. So at the beginning of this method, we need to add our base condition. If the index that we're visiting equals word the length, that means we're visiting the last letter for this word. Now you might say, but Mosh, shouldn't that be word the length -1? In this case, no, because the first time we call the remove method, we're giving it the root of our try. That is the empty node. If you simply write down the flow on a piece of paper, you will see it for yourself. But let me prove it to you. So if this index equals the length of the word, we are at the last node. So I'm going to print root.value and then return immediately. So let's not worry about the deletion. Let's just make sure that we're visiting these nodes in the right order. So this is our base condition that terminates the recursion. And as I told you before, we need post-order traversal. So we visit each child first and then come back to the root node. Post-order traversal. So as part of visiting this root node, I just want to print root.value. Now, when we run this program, we should see the characters coming out in the reverse order. That will prove that our recursion is implemented properly. We're visiting these nodes in the right order. Then we'll come back and implement the delete operation. So back in the main class, we have two words here, car and care. Now let's remove the car. There you go. So these characters are coming out in the reverse order. First, we visit the last node, that is the R. We're done with our recursion here. Then we go back up to its parent, that is A, and then the C. Now that we're confident that our recursion is working properly, let's go back and implement the delete operation. So when we're visiting the last node, what should we do here? We should remove the end of the word marker. So we set root that is end of word to false. That's all we have to do. We cannot physically remove this node at this point. We have to do it later when we come back to its parent. So in our post-order traversal, after we come back from visiting the child, now we're at the parent. So we have to check to see if this child has any children. If it doesn't, and it's not the end of another word, we can physically remove this child. So if child, now we have to see if this child node has any children. One way is to call getChildren, then check the length and compare it with 0. But I would prefer to create another method like hasChildren or isEmpty. That makes our code more expressive. So back in the node class, let's add another method. Public boolean has children. Now here we return children dot is empty and then inverse the result. So if it's not empty, that means it has at least one child. Now we can replace this expression with if child has any children, well, more accurately, doesn't have any children, and it's not the end of another word. Now we can physically remove it from our tree. So we tell the root node to remove this child. We don't have this method yet, so back to the node class. Let's add another method here, public void remove child. Now we can give it a node object or a character. I would prefer a character. That would make the interface of this class more consistent, because earlier we declared this method add child, which gets a character. Similarly, we have get child, which gets a character. So for consistency, I would prefer to pass a character here. Now all we have to do here is to call children.remove and pass this character as the key. Now back to our remove method. So we tell the root object to remove its child. What child? This character over here. That is the one that we're currently processing. So this is our implementation so far. Let's test it and make sure it works. Back in the main class. So we have two words, car and care. We remove the car. Now let's see if I try contains the car and the care. Take a look. So we don't have the car, but we have the care. In this case, we kept all these nodes in our try, but we removed the end of the word marker from the R. So now it's only the prefix of the care. Now, what if we remove the care? This time we have the car, but we don't have the care. Now, what if we try to remove a word that doesn't exist? Let's say book. We don't get any exceptions and our tree is not affected. What if we try to remove an empty string? We're still good. What if we pass null here? We got a null pointer exception that happened over here in our base condition. So I would rather not to pollute this method and instead do the null checking in our public method. So if this word is null, there's no need to do all these recursive calls. So we're going to return straight away. Take a look. That is better. So this is how we implement the delete operation.